Hi and welcome. My name is Matt Gaffney. Today's talk will be an introductory talk into electronic flight bags. We'll be covering their systems, the software, the hardware, approval processes, and just basically a zero to hero on electronic flight bags. Now bear in mind, I'm not a pilot. I don't use these day in, day out, and I've never worked in flight operations either. So I'm giving you this from the perspective of an outsider as well, which means I will cover things in a way that's designed for the intended audience, i.e. Security researchers and InfoSec professionals. I'll also have a special appearance. We've got a pilot instructor who'll be giving her input as well on electronic flight bags and how they've been such a revolution in the cockpit. So this is the topics we shall cover today. We'll cover the definition and usage. I'll give my pros and cons. There are probably many more out there, but these are the ones that I feel are most pertinent. Hardware, software, the connectivity into the aircraft when they have them, or not to the aircraft as the case may be. Like I said, accreditation, the typical functions and content that they do. I'll be demoing some EFB software I've managed to find on the internet. And then we'll finalize with the pilot instructor's view. So an EFB can be defined as any device or combination of devices primarily intended for flight deck use. They have been a revolution for pilots and they are still rapidly evolving. As the name suggests, they replace the large and cumbersome and often heavy bags which used to be full of paper-based manuals, which weighed a lot. As well as the obvious fuel cost saving, there is the added advantage of the crew not exposing themselves to injury whilst handling the bags that the paperwork used to sit in. Depending on the type of EFB, they can perform a variety of functions, such as perf or performance calculations, V1, VR, V2, MDL. We'll go into each one in detail later. En route and on ground navigation, and that will obviously generally require a GNSS GPS feed. A documentation and reference library. Pretty much all EFBs do this. That is kind of the cornerstone of an EFB, really. And an interesting one as well is the quick reference handbook, or QRH. This is important for emergencies, and I'm seeing this more and more in electronic flight bags. But they also give things like NOTAMs, weather information, and NOTAMs is a notice to airmen, and they can include warnings of potential threats or closures of airspace that the pilot might need to navigate around or avoid. They can also be used for fuel calculations, weight and balance, and this is important to get right, as an overweight or improperly balanced aircraft can be catastrophic. They also include bespoke applications which complement the airline operations, so long as they achieve the relevant approvals. And the main advantages of EFBs are the reduction and elimination of paper-based manuals. And the documentation is also faster to access, so you can get quicker access to the information. All of this helps lower turnaround times for an aircraft and reduces workload in the cockpit. Now, a lot of non-pilots may not understand the importance of that last phrase. Many incidents, which include pilot error, cite cockpit workload as either the main or a contributory factor. So this makes EFBs not just effective in reducing costs for an airline, but they also can help make flying safer. So we've already mentioned how EFBs are lighter, but that's not the only advantage. If used correctly, they provide faster and more efficient access to documentation. And the reduction of paper in the cockpit doesn't simply save weight and reduce carbon footprint. It can reduce the workload of the pilot. One thing you will hear often in airlines is that aircraft don't make money while at the ground. So reducing turnaround times can be a significant way of increasing return on investment and revenue for that aircraft. On the downside, EFBs require management. You cannot just install software on a device and issue it to the pilots. It requires approval from a regulator and an ecosystem to ensure its safe operation and maintenance. Updates need to be tested and coordinated to ensure that the right data is available to pilots. The wrong mapping, documentation, or checklists can have significant safety and operational consequences. Needless to say, that introducing new digital hardware to operations also introduces new potential attack vectors that require protection. Class 1 and Class 2 devices are not much different from a typical iOS or Windows platform. The worrying part is that these devices are often built and put into service by flight ops with little or no input from IT or InfoSec departments within an airline. And this can lead to poorly configured or insecure devices which pass approval, but which introduce vulnerabilities into IT systems in the cockpit. And we'll talk more about approvals later on. So hardware categories have different names, but depending on which regulator you sit under, I've included both with some general characteristics. So Class 1, also known as a portable EFB, and these are typically small, used for corporate activities as well, such as email, intranet, and calls. They have no connectivity to the aircraft, and they are classed as PEDs, a portable electronic device, so they must be stowed for takeoff, taxi, and landing. A Class 2 or pilot or a plane attached EFB, now these connect to the aircraft information systems domain with typically with a one-way feed of information, of data from the aircraft control domain or the avionics. And they can be integrated with the cockpit displays, which is a really handy feature when you're trying to design mounts that maybe have a suction cup to a window and achieving approval, because you still need approval for that. It's in the cockpit. It can be much easier to just have a bit of software and a bit of hardware which displays the EFB screen on the multifunction display in front of you. And Class 1 and Class 2 devices, the build is the responsibility of the operator. It's also worth mentioning that Class 2 EFBs have very different threat profiles depending on whether they are pilot or plane attached. While plane attached EFBs are considered part of the MEL, the minimum equipment list, and tracked as an aircraft part, they are always under the control of the airline with coordinated and tracked movements between locations. Pilot attached EFBs are not. They enter and exit the cockpit when the pilot enters or leaves the aircraft. They are very likely to connect to all sorts of networks in hotels, cafes, and airports, so that the pilot can update software, nav databases, NOTAMs, read corporate emails, or even surf the internet. Now, do all operators restrict such EFBs or secure them appropriately to the threats and risks that that presents, or even in accordance with the rules and recommendations set out by regulators? It's a good question, given that so little of the EFB regulation covers security. And a Class 3 or an integrated EFB, they are built as part of the aircraft control domain or the avionics. There's no connectivity outside of the ACD or the aircraft, and the build is responsibility of the manufacturer. And they may be maintained by the operator, but the manufacturer is the person responsible for building them and certifying them as part of the avionics. So like I said, Class 3 EFBs are certified as part of the avionics, so the operator has next to no ability to make changes unless they wish to go through the trouble, expense, and pain of recertifying it. Even though Class 3 EFBs sit in the ACD, the ones that I have seen are also logically separated from the core avionics. And you have to interface through many different modules inside the ACD before you can bridge the gap between a Class 3 EFB and avionics systems that control the flight surfaces. So even attacking a Class 3 to affect the controls is not that straightforward. Software types. Type A, like I said, the storage and display of documents, or being a document and reference library, is the cornerstone of an EFB. That's the minimum real functionality you will see in an EFB device these days. Type B applications, these also include all of the Type A functionality, but they also include things like perf computations. They may also access the internet whilst on the ground and or in flight. And they may also be able to receive one-way data from the avionics. And this is the most common EFB software type. Class 1 and Class 2 EFBs, like I said earlier, are built by the operator, and as such, they are not the responsibility of the manufacturer, even though the manufacturer often provides some or all of the software that runs on the device. For EFBs running Type B software, this is where things can get a little bit blurred. According to EASA and FAA approval processes, any vulnerability in the software that could affect the operation of the EFB, regardless of who coded it, is the responsibility of the operator to mitigate. At the same time, any details on vulnerabilities may or may not be passed on to the operator. They often just send them a series of recommendations for EFB security, or even none at all in some cases. So how many operators routinely perform vulnerability assessments, code assessments, or reverse engineer the software and perform penetration testing on EFBs in the software? If it's the responsibility of the operator, then surely that's something that airlines should be doing on a more regular basis. The Type C software. Now these can control or affect the control of the aircraft in flight. They can send data to the avionics, so they can bridge that gap between the aircraft information systems domain and the aircraft control domain. Now, I'm not sure whether it can receive ACARS over IP, as that would suggest a data route from the AISD into the avionics, which degrades the integrity of the ACD. I'm doing more research in that area at the moment. But one thing I can say is there are no current approvals that exist for Type C software. So all you're going to find is Type A and Type B that's out there in the wild right now. However, I am seeing some manufacturers offering functionality for bidirectional EFB communications. So whether that's with the FMS or not, and how it's done, I don't know yet. But like I said, I'm still researching. Connections to the aircraft are varied. EFBs are basically computers, so their network connections are typically the same. Outside of some rare cases involving Class 3 EFBs, you're unlikely to find any connections like ARINC 429, ARINC 825, etc. In the implementation in EFB. However, you may find ARINC 664, which is based on Ethernet anyway. Ethernet is pretty common with aircraft-attached EFBs, and they are usually very insecure, as they often leverage the physical security model of the cockpit. I.e., if you can get into the cockpit, why would you try and attack an Ethernet connection? Because there's so much more damage you can do. However, that does lead to some cases that I have seen with very poor security. Some do have basic authentication between an EFB device and the aircraft information systems domain, and that might be something like IPsec PSK. But I've yet to see any encryption or serious authentication on Ethernet connections. Data often goes between the EFB and the AISD in the clear with no encryption. And I've been told this is because implementing encryption in a semi-isolated domain is too difficult, apparently. Wi-Fi in the cockpit is growing in popularity amongst operators and manufacturers. Why not? It's easy to do. Implementations are generally good, with WPA2 PSK being the most common lowest security option I've seen available, with WPA2 EAP commonly available as an option to operators. However, again, it sits with the responsibility of the operator to secure this connection and to configure it properly. Weak PSKs and poor certificate management can introduce weaknesses which could be exploited by attackers. This is why it's important to include IT and InfoSec into the development of solutions in the flight operations department. The staff there will know flight operations like the back of their hand, but they may not understand the risk properly. And this is where IT and InfoSec can come in and make sure that correct processes are implemented and that the build is done correctly to make sure that everything is well managed. And then finally, LTE or 3G, 4G is also found in EFB solutions. If you're using an iPad, for example, all you need is a SIM card. Almost always in class 1 and sometimes in class 2, you'll find this implemented. In both cases, they introduce another vector that can cause problems for security. That said, they do provide excellent data connections for updates and other applications on the device. The alternative is that the connection on a class 2 device goes through the ground systems via SATCOM and then out to the internet through a DMZ. And you can imagine how slow and low the data throughput is on that, and of course the high latency that SATCOM gives you. So, approvals. Class 3 or integrated EFBs form part of the aircraft certification process, and they're under the remit of the manufacturer, like I've already said. So we're not really going to cover those here. They're not included in the EFB approvals process for the operator. So, however, on the other hand, the Class 1 and Class 2 do sit with the operator, and they do go through, or they're required to go through, an approval process set out by your local regulator. Now, the FAA has defined AC 12076 and the EASA AMC 2025 as one such means by which to gain approval. And there are others, but these are the most common. And they both go into depth on the design of the GUI, the size of buttons, usability, like I said, mounting brackets and suction cups and safety, accuracy of perf calculations and how the design and function of the EFB should not have an impact on safety. They go into lots of detail and all of that. But as you can see, both include a section on cybersecurity, but nowhere near the detail that you would find in these other subjects. Not only is the word count low, it's vague and frankly lacking in substance. The most worrying part, though, is that the approval process puts the owner entirely on the operator when the software is produced by the manufacturer. This results in, or can result in, a lack of accountability on manufacturers of EFB software, as the operator being responsible for mitigating any vulnerabilities in the software, but software they didn't write. Now, I'm not saying some manufacturers are using this as a green light to make EFB software that favors ease of development over security, but at times it certainly appears that way. The approvals mechanism seems to focus a lot on all potential mechanisms by which the wrong data can be presented to the pilots, normally through error or poor design. There is a lot of detail in scenarios where fat fingers, user errors, physical or environmental influences can have a negative effect on EFB operation, leading to a potential safety situation. Where it seems to fall short is the scenario where an attacker may wish to have the same effect, but through technical manipulation, i.e. hacking. It's no good making sure the buttons are the right size and the results are accurate if the basic security measures are not taken when developing EFB software. That said, there is some help for operators available, and I hope they don't mind me giving them some praise. Airbus have a publication giving security recommendations for EFB, which is very good, and actually applies to most, if not all, non-integrated EFBs, regardless of manufacturer. It doesn't cover everything I would go into to secure an EFB, but it is an excellent starting point for anyone who has yet to consider protections on EFBs from cyber attacks. So, what is a UFB used for exactly? It should not be a surprise to learn that pilots love checklists and procedures. They drive safety, and their implementation is driven by safety. And this ensures that all actions are performed for key stages of flight. They are completed as a team between the captain and first officer. One will read off the list while the other performs it, and then the first guy will literally tick it off the list. And as well as normal cockpit operations, they are essential in troubleshooting and emergency procedures as well. The QRH, or Quick Reference Handbook, is used in emergencies and gives pilots access to the checklists they need to handle in any scenario they find themselves. These are typically still paper-based, but I'm seeing a lot of EFB software providers advertising functionality for an eQRH. Now, as the QRH forms part of the MEL, or the minimum equipment list, I would imagine that this would be important to get right. Airlines can also get critical information from their operations center and passed to the pilots electronically. Veteran pilots will remember when they had to dip the tanks and perform some manual calculations and then literally order fuel straight from a guy in a truck and pay with their credit cards. Modern aircraft systems give very accurate readings, and fuel calculations can be done on EFBs. Weight and balance is critical to get right. Incorrectly balanced aircraft can lead to very dangerous situations, which are not apparent until during or after takeoff. Those of you who follow the news will have seen an article in the UK recently about an incident where an airframe on a commercial flight was changed prior to departure, but for whatever reason, this change wasn't taken into effect and the weight and balance remained the same. And the change that happened resulted in an aircraft which was a lot more front heavy than it should have been. And the pilots didn't notice this until they were rolling down the runway, and the aircraft twice failed to respond to the pilot's input, i.e. they tried to pull back on the stick and they weren't going anywhere. So they were forced to implement an emergency procedure, engage TOGA, which is an auto throttle setting used in takeoff, go around, TOGA situations. It's literally a couple of buttons on the throttle stick. And that requires a lot of thrust. So the aircraft takes over controlling the thrust of the aircraft and gives it whatever it needs. Engineering paperwork can also be done on an EFB. Typical MROs or maintenance and repair organizations use paper with carpet triplicate to report issues, complete diagnosis, and track repairs. This paperwork is key to maintaining the airworthiness of the aircraft, and any errors can lead to an aircraft being grounded until it is resolved. In this situation, you will typically require the engineer to meet the aircraft, recover the paperwork, start diagnosis, and then leave to get any parts required, return, and then fix the problem. Driving around airside is not like heading down to the shops for a pint of milk. It takes time. There are long one-way systems and slow speed limits for obvious reasons. Now, if you can have the data sent digitally from the EFB to the engineers on the ground whilst the aircraft is still in flight, they can meet the aircraft at the gate with a diagnosis and parts ready on hand. And this again leads to the shorter turnaround times and a reduction in delays. En route and terminal navigation is also important to get right. Air traffic control will vector a pilot to a location, but the pilot also needs to know where other airports are, waypoints, exits and entries off a runway. In the past, these were held in large ring binders, which are heavy and require one of the pilots to get out of their seat to recover if they have to go to a new binder, for example. And this is not ideal in an emergency. So having this information available digitally at the fingertips of the pilot while still sat in the seat without having to move is a game changer for pilots, especially when they are faced with an abnormal scenario. And one of the key functions of an EFB are what are known as the perf, or performance calculations. These provide the pilots important data for critical stages of flight. Situations leading to the wrong data being given to pilots can and has led to incidents where safety was compromised. And when this happens, an investigation is opened, regardless of whether the pilots had to take corrective action. Worryingly, there have also been incidents where pilots are unaware of having the wrong data because they subsequently take off or land on a runway which is more than long enough, and they don't notice the problem. However, it would be wrong to suggest that there aren't additional safeguards in place. The aircraft has stall sensors, warning indicators, and other technological items. And then you have the pilot's experience, and these are all at play. And at the end of the day, the pilot will just fly the aircraft and use airmanship if something is not quite right in the data they are seeing. Here is a short demo of some EFB software. I was unable to find an operator willing to let me show you around their EFB solutions, and any commercial EFB software providers I managed to get the attention of wanted to do a full commercial kind of advertisement. So, and that goes against our ethos. So I'm stuck here with the open source and demo route. And first up is FlySmart Plus from NavBlue. Now, this is a very popular EFB software solution, used mostly on Airbus aircraft, but it is available for others. And they have demo versions available for anyone to download on their iPads. And it simulates the inputs and outputs for takeoff and landing perf calculations. So let's go ahead and start this up. So the first things you have to do is you put in a flight number. We'll just put in something random, and then your starting point, your destination. Obviously, it uses demo data here. And the first thing you do is select which runway you're on. 0927. Makes me think it might be Heathrow. And I'm going to go for a shorter runway there than the full length 27. You input your wind. So we have the direction it's coming from, 10 degrees. The speed of the wind, and then the gust speed. So obviously these are important for pilots to take into account, and there will be limits on what can be put in here. So what we've said here is that when you put in a value, it has to be correct. So here the EFB itself is saying, well, you can't have a tailwind stronger than 10 knots, therefore change it. And there we can see on the EFB software, what we have is an arrow indicating where the wind is coming from. And then OAT, that stands for outside air temperature. That's fairly straightforward. It has an effect on the aircraft. The warmer the air is, the less dense it is, therefore the less lift you're going to get off the wings. So it reduces the amount of the maximum takeoff weight of an aircraft. Air pressure also has an effect. Again, the higher you are, the less dense the air is, same effect. And then all these other factors as well, such as runway condition and icing. Takeoff weight, obviously, this is quite important to get right. If you try and put in, the wrong value, it will stop you from doing so. And there are also the controls and checks on the data going in. So what it won't let you do is put in a value that's too high or too low. But if it is within range but could cause stress on the aircraft, it will ask you if you are sure you want to do this. So here we're just playing around with some values. Let's try and 40. Like I said, it's lower than it would be normally. So what we're going to do is put in something that's pretty normal, which is 68 tons. And of course, this is an A320, so it's quite a small aircraft. We configure the flex, which is a reduction in the thrust, to standard. And we put in optional conf and normal air condition. So we run the computation, and what it's telling us is that actually on the current configuration of runway and these conditions, we cannot take off. And it's saying the limitation here is runway. So what we will do is change some of these. So we shall increase the air pressure a little bit. We'll keep the weight the way it is. And what we'll do is we'll change the wind a little bit. So instead of a crosswind takeoff, we're going to have a, let's make it a headwind takeoff. There we go. You can see the arrow has changed. We're now flying, or taking off into the wind. We run the computation, and these things aren't fast. And there we go. And oh, we've actually got a toga aircraft. Sorry, toga takeoff. Toga is the takeoff go around. So that is obviously a high thrust. There's no reduction in the thrust on the engines. But it gives us the V1, VR, V2. So as I said earlier, V1, that is the go, no go speed. Once the aircraft reaches that speed, if there's an issue, you take off regardless, or you carry on regardless. VR is rotation speed, so that's the speed at which the pilot will put input into the stick or pull back on the stick in order to make things go up. And then V2 is like a minimum climb speed, really. On some aircraft, it's also known as the speed at which you can still gain positive lift with one engine. And then it gives you limitations here, so takeoff weight. So that's the reason for it going toga. And then it actually says what the maximum takeoff weight could be in this configuration, which is 68.5 tons. So yes, we are very close. And I would suggest or suspect in this scenario, the pilots would double check all of their figures again. Because they are so close, they would double check that these inputs are correct. They would double check their takeoff weight just to make sure they haven't snuck in half a ton somewhere, or even worse, a ton. And then if there's anything needs changes, they would rerun those figures. So switching to landing. So same thing again. Put in a bogus flight number. Put in the same runway parameters or the same start and end point. So we program in, same things again. So the wind has shifted, and but it's calmed down a little bit. We have a crosswind landing, but with a gentle wind. The outside air temperature is a bit lower. Typical air pressure. So yeah, so landing weight. Now this will come from your takeoff weight. And then in the cruise performance calculations, there will be a calculation on how much fuel you're going to burn. And from that, you can work out what your landing weight is going to be. We run the computation. In real life, it is this slow as well. So here we go. So what we have here is a set of results which gives us landing speed, the gradient, the landing distance calculation, and then what the margin is beyond that. And also will give you your maximum landing weight based on the current conditions. And that is 69.2, which is well above our calculated 60. So that wouldn't be an issue. But if we change some of these parameters, for example. So let's give this a strong crosswind with heavy gusts. Run that again. And, we're still going to get a landable configuration. Obviously, if we increase the weight a little bit, then that's going to change things. Now, we're going to be an overweight landing. We're going to say yes for for purposes of this demo. Run the computation, and as you can see, what it's saying is that you should be okay, but you haven't got any buffer. Therefore, you are above the runway length for that runway. So hopefully that shows you a bit about the perf calculations and the type of inputs that the pilots have and the outputs they get from them. So for navigation, I'm using an EFB software that is typically used for general aviation, but which also behaves very similar to that found on commercial aircraft. And this is a product called RWY, or Runway, by Oz Runways. It was the only one I could find which didn't crash on BlueStacks. So I'm going to talk you through it here. So as we can see, what we have is, you know, a very typical, you know, mapping which you find, and the ability to consult things like weather overlays, which is open source. It comes from Windy, but it also allows you to identify, you know, or select airfields, input them into a flight plan, and you know, obviously you can see we have codes here on the right for airports. And they're very different from the codes you'll find as a passenger. So, for example, Heathrow is LHR for, you know, when you're searching on Kayak and other flight websites. But for a pilot, it's EGLL. And here is the documentation you'll find for Heathrow, and it gives you details of the runways, the elevation, the height, you know, the lat long. It will give you obstacles, the height of the obstacles. The runway physical characteristics. Even the intersections with which they take off from. And then what we can do is we can manually search for an airfield. So here I've put in Heathrow, I've added it to my flight plan. And from my current position, it's given me a direct line to fly as well. It allows you to do some performance calculations, but these are based for you know, small, probably single piston aircraft, so it's not really much use to us in this context. As you can see there, the direct line to fly is flashing green, but let's put in a second destination. And let's go for Blackbush. There we go. It's giving us our route. It's giving us a distance. It's giving us a vector. And on our flight sheet, what we've got there is, you know, typical airspeed, your track, heading, ground speed, distance, and then your estimated times. Now, if you look at the briefings for each of the aerodromes, just gives us a quick briefing. Give us basically meteorological data. If we go to airfields, what we do get access to, so this is the general stuff. If we then look at all of the documentation, we get some interesting stuff. So we get some ground charts as well. Now, obviously, these are important when you're taxiing, because you will be, you know, given a route to follow by ground control, and so they will say exit at A5 and, you know, take L2, etc., etc. And these are lines which you will follow on the ground to follow that route until you get to your gate, obviously. You'll see here, obviously, we don't, the pilot doesn't see gate number. What they see is gate numbers that a passenger would see. They see numbered positions. What will also be in there is some areas of potential conflict or issues with descriptions, or hotspots as they're known. You know, so this is areas that might have had incidents in the past, or they're having, or there's a defect or something along those lines in that area, which pilots should be aware of. And then here we have holding patterns. So here we have, for Heathrow, we have two. One which is over Biggin Hill, the other one over Ockham. And bear in mind that Biggin Hill's on the other side of London, pretty much. But once an aircraft is released and heads towards the runway, it's probably only a matter of minutes before they're on the ground. So the speeds at which, even in landing configuration, these aircraft are going at is quite significant. And then obviously the point when you reach the X there is you should be on ILS. So you'll pick up ILS and you'll be guided in by the ILS and by the tower if needs be. Anyway, I think you get the point. There's lots of interesting information here, and all are very useful of use to the pilot. If you can imagine all of this being in ring binders previously, that was a lot of data. And now it's all available electronically at the touch of a finger, which is very helpful for pilots, reduces burden, reduces cockpit workload, and in turn increases safety, as well as making things a bit faster and cheaper for the airlines to run. So going back to our route, you see how I've manually inputted a location here. Anyone thinking about doxing me, I'm not that daft. This is an aerodrome which is far away from my house, the aircraft is currently right at the end of that runway at Fair Oaks, which is just north of Woking. So looking at Farnborough, which obviously used to be RAF Farnborough many, many years ago, we have the same things, and it gives us all the information that we need. So finally, we are privileged today to have input from an experienced airline pilot instructor. I have very little experience flying aircraft, so it's an honor now to hand over to Alex, who will give you her input on EFBs.
Hi, I'm Alex, and I'm an airline captain with 20 years experience, from flying light aircraft, turboprops to jets. I'm also a type rating instructor and examiner. I'm going to talk to you about the EFB from a pilot's point of view. Electronic flight bags, or EFBs, have transformed how pilots operate. The landscape has changed significantly over the last 20 years, and none more so than the pilot interfaces, and one of those big areas is the EFB. You've already seen the type of applications that are generally seen on the EFB, and the ones which have had the greatest impact on the pilots are the performance elements, the charts, and the operations manuals. On the flight deck, we generally use two independent systems. One is generally operated by the captain and one by the first officer. And this allows independent calculations and cross-checking of safety critical information. So taking the performance element, the EFB software calculates various speeds. It calculates V1, which is the go, no-go speed. It's the last point at which I can stop, take off on the runway with sufficient runway ahead. Past that point, I then have to continue with the takeoff. The next point is the rotate speed, which is the speed that I actually lift off the runway. And then the V2 climb speed, which gives me a climb gradient to miss any obstacles at the end of the runway. It also produces a flex thrust, which is basically a reduced thrust takeoff. This is something that we use on a day-to-day basis. Most takeoffs don't require our maximum thrust setting. So the EFB, or the performance calculation, calculates what the actual thrust we need to depart with those conditions of the day. This can therefore increase the engine serviceability and therefore safety, and it increases engine life. It also calculates the trim of the aircraft. When I started flying, certainly in the turboprop world, we actually use graphs to calculate our load and balance trims. Obviously, these are now done very accurately as opposed to me with a pen and paper. Not only did I have to do graphs of the trims, but performance was calculated using paper performance tables, which were very generic. They obviously had high margins of safety built in, but as a result, they weren't particularly accurate. They were safe, but not accurate. The whole point of having the EFB, or having it calculated electronically, is it means that we can now improve the accuracy of the figures that are generated, and it gives me a much more realistic idea of the actual performance of the aircraft on the day. It also enables us to operate in a wider environment. Often airports, which would have been limited before due to these generic tables, we now know that we can operate under certain conditions, so it gives greater flexibility to the operator. Company procedures do vary, but they all rely on the principle of both pilots independently cross-checking data. And that is the thesis behind multi-pilot operations, that we continuously check one another's work. This is no more so when it comes to safety critical information such as performance. The way we normally operate is these performance calculations are calculated independently on separate systems, and then we check with each other and also check with the expected or estimated figures. And any errors or any gross error differences have to be explained away or recalculated. The other way that it's revolutionised is the use of the charts. EFBs generally have all the charts loaded onto the applications. And again, this has revolutionised how we operate. Now my route can be loaded in a matter of seconds in some instances onto the EFB. This now gives me information along my route for safety critical things such as terrain and minimum safe altitudes at which I can descend the aircraft to and know that I will be above any terrain. This now gives me very good pictorial representation very quickly. Also, it shows me kind of where the airports are. So if I need to divert for many reasons, I can now just click on a symbol and it will bring up the airfield information, such as the approach aids, the runway length, and all the information that I would need, frequencies and such, to make an approach at that airport. Even when I started flying jets, and as close as 10 years ago, all this information used to be held in separate documents, which were in ring binders, which were stored in a big crate, normally on the flight deck. As you can imagine, this was very heavy. It was also very labour intensive to keep those amended. And it also it wasn't very user friendly. If I wanted to find an airport, I had to physically get up out of my seat to go and find that airport. Again, I can now just do it at the touch of a button, so it gives me a lot more flexibility and obviously can have a lot more information to the pilot. The other aspect that has changed is flight crew operations manuals. Flight crew operations manuals contain supplementary information. This is extra information other than the systems give you, and obviously your basic knowledge that you need to know to actually fly the aircraft. It delves into the systems in a bit more detail. And this can be regarding abnormal emergency situations as well as normal situations. And it also gives us limitations and performance tables. Again, going back to the good old graphs that I would have used originally. Again, we used to carry these as hard copies, but they again used to be amended, whereas now they're all at a touch of a button. Often finding information in these paper copies was labour intensive, whereas obviously now I can use a search function, which is much quicker. So having established that they are actually useful and they provide the pilots with lots of safety critical information, it stands that if they're going to be used in flight and incorporated into kind of our day-to-day operations, then we need to have redundancies, and they obviously need to be part of now the aircraft equipment list. All airlines or all aircraft have what's called a minimum equipment list, an MEL, and these are items which are required to be carried by the aircraft. Alternatively, they can actually have items which can be dispatched with, but under certain criteria. And the MEL actually states the electronic flight bag is one of those items where we need to have it on board. There are various redundancies with it, so we can have, in certain occasions, both the software or the hardware inoperative, and there are restrictions that are placed on us. So those might be things such as you can operate with one, but if you operate with one, it has to have a fully serviceable charger, and you also have to have, in the case of only operating with one EFB, you have to have a functioning terrain avoidance collision system, so that should you need to descend rapidly and you don't have the information on your chart, obviously the aircraft systems and the display is available. So there's multiple redundancies built in at all points. We also carry hard copies of what's called the Quick Reference Handbook, which is the QRH. And again, these have performance tables. So if I needed to work out gross, again, the big charts that I used to use for rough figures, which have plenty of margins in them for both stop distances, landing distance available, and also speeds, I can actually go into the QRH and all that information is given me. So although the EFB is very user-friendly and very easy to use, we actually do have redundancy built in. And normally there's at least one or two, if one system's down, we have at least two other systems that we need to have as backup, be it a paper copy, or alternatively another functioning EFB. Also, airlines now are going along the lines of issuing crew with personal devices, and these manuals are loaded on the personal devices. Part of company procedures is to keep these things updated. So although they don't make up part of the aircraft equipment list, actually, again, redundancy is built in. So as I operate, although I have two EFBs with fully loaded charts and flight plans, I now have my own personal device as well, which again has a duplication of information just in case I need it. Hopefully that's given you a bit of an insight into how a pilot operates using the flight bags and the kind of good user-friendly interfaces that they have. Thank you.
Thank you, Alex. So that's all we have for you today. Like I said, the aim of this presentation was to give you an introduction to EFBs and what they're used for. I'm doing research into their security and how operators can improve the security posture on EFBs. And this will be covered in future talks and releases. Thank you for tuning in. Alex and myself will now be available in the Discord channel for questions and answers.